My name is Chris Budai, and I'm a project manager with the U.S. Army Corps of Engineers, Portland District.
And were you with the Army Corps of Engineers back in 1980 when Mount St. Helens erupted?
I started with the Portland District in 1985, so I came on just when they holed through Spirit Lake Tunnel, and I took over that project ever since. So.
Right. Can you give us a little bit of background about why the Spirit Lake Tunnel needed to be built?
Yeah, the eruption of Mount St. Helens resulted in a huge landslide that blocked the natural outlet to Spirit Lake. And so FEMA was put in charge right away, and they called on the Corps to help them address the situation that there was no outlet for Spirit Lake. A bunch of material went into Spirit Lake and raised the lake about 200 feet or more. And so the lake was spread out a little more and higher in elevation, and there was no outlet, and it was filling like a bathtub. And so the Corps was tasked with figuring out how do we keep the lake at a safe level right away, and then how do we provide an outlet for the lake for a solution. And do you want to know what we did, or? Okay, so the immediate how do we address the rising lake level with no outlet? The Corps decided to fly in a barge and 20 pumps and pump the lake to keep it at a safe level, and discharge the water through a pipeline up and over the blockage and back into the North Fork Toutle River, because Spirit Lake is the headwaters of the North Fork Toutle River.
And once you selected the location to place the tunnel, was there a specific reasoning behind that spot?
There were many tunnel alignments that were looked at. We looked at other alternatives. Do we want to pump permanently? Did we want a gravity-fed pipeline from the lake up and over the blockage, through the blockage? And so we looked at all of those various alternatives before ultimately settling on the tunnel alignment where it's located, which is through Harry's Ridge. So it serves as an outlet for the lake. It's down 40 feet to allow for an adjustment in the intake elevation, because it wasn't certain really what was needed in the future. And the tunnel exits out the other side of Harry's Ridge into South Coldwater Creek, that flows into Coldwater Creek, that flows into the North Fork Toutle River. So it's basically a little detour to get the water out of Spirit Lake. And the one thing also was that the water would then not be going into the area where the landslide was, a very unstable area. We didn't know the characteristics of it, and we didn't want to erode that and cause a breakout, which would be a huge mud flow set downstream. So we really wanted to avoid that kind of risk.
And just addressing some concerns I've heard from other people living in the area. They're kind of curious, like if we had, a large earthquake or another volcanic eruption, could the tunnel stand up to something like that? Like, are there any imminent worries about that?
I think it could. It's performed beautifully through all the earthquakes and eruptions we've had since 1980. Of course, none of those are as big as the 1980 eruption, but one of the driving forces for choosing the tunnel option as opposed to an overland option was that the tunnel would be less susceptible to earthquake damage and failure from a volcanic eruption. As I mentioned, they lowered, there's a 40-foot shaft that the water from the lake drops down and then into the tunnel and exits. So being buried 40 feet down kind of protects the tunnel from those events. And the theory is that it would still be functional during and after another eruption or earthquake.
And from what I've read, this it's 11 feet wide, a little over a mile and a half long. Can you tell us a bit about what went into constructing the tunnel?
Sure. It was very fast track, and we had a lot of good people putting plans and specs together, and a good contractor came on board, a joint venture, and they were given the option to drill and blast the entire tunnel or to use a tunnel boring machine. And they proposed to use an 11-foot diameter tunnel boring machine. The very first 300 feet and exit are horseshoe, drill and blast horseshoe shape tunnel configuration, but everything in between is the circular 11-foot diameter tunnel. And we knew through exploring the alignment of the tunnel that there were 5 major shear zones the tunnel would cross. And at each of those shear zones, we knew additional support would be needed for the tunnel. And so it called for steel rib sets to be installed with precast concrete invert slabs for those steel sets to rest on. And so they were installed at each of the 5 shear zones. The major shear zone is smack dab in the middle of the tunnel. It also happens to be right where the geology changes from a tufaceous volcanic rock to basaltic volcanic rock. And right at that contact, you have the major shear zone and the tunnel alignment. So it's like a triple alignment, and that has been kind of our nemesis. We've had to go in repeatedly to repair that area, and they had a very difficult time during original construction getting through that area because there's clay gouge and the tunnel boring machine bores through rock, not clay gouge. So they had to kind of drag the TBM through that area of tunnel and put in lots of shoring to keep the tunnel open and safe. But they got through it, and so that's kind of the drama of building the tunnel, was kind of that area and the other shear zones. The rest of the tunnel's in pretty good rock. It's unlined, and it's a non-pressurized tunnel, so water flows in the lower third of the tunnel, open air, and we inspect it every year with the Forest Service, and any little patchwork or repair work that needs to be done, we let the Forest Service know, and we put a contract together and button it up so it can pass the water and function properly.
And would you feel comfortable elaborating just a little bit more on some of you mentioned it's been kind of like a nemesis for you guys with some of the structural repairs you've had to go in and do over the years. Can you elaborate on that a little bit more?
Yeah, for the most part, we've had to go in and do what I call concrete patchwork repairs, and a contractor will come in from the downstream, and we close the gate. They come in and they'll place concrete to patch holes and make sure it's buttoned up, because you don't want water getting in behind the rib sets and the precast concrete slabs. And so we've had to do that numerous times. That's just routine maintenance. But on a couple occasions, we had some major repairs, and one was in 1996, and the steel sets sheared and failed, and we had to go in and with a road header that time, and the power plant was outside the tunnel, and the road header tracked into the tunnel, and they excavated in between the existing failed steel ribs and installed full circle, bigger, stronger steel rib sets, and that restored the integrity of the tunnel. So that was about 100-foot repair there, if I recall. And then again in around 2014, I think it was, when I inspected the tunnel, we saw the bottom of the tunnel had heaved up a little bit, and we were already in an area that was kind of tight because there was a lot of rib sets and shotcrete and stuff closing the diameter of the tunnel a little bit, and we don't want to pressurize that tunnel. So we put a contract together and installed, I think it was 32 feet of tunnel, 16 new rib sets, where we excavated again and opened up the tunnel, put in new steel sets to restore the integrity. And that worked well. That was done in the winter of 2015-16 timeframe, I believe. And so those 2 repairs involved installing new rib sets, which involves more equipment, more cost, and it's a little more elaborate than just going in with a wheelbarrow, mixing up concrete and patching the tunnel. So we had those 2 repairs. And we do recommend to the Forest Service that they consider doing a rehab of the tunnel, where those areas were both in that triple junction area I described earlier, where you have maximum overburden, change in geology, big shear zone through there. And that shear zone is about 300 feet wide. So we address the lower 100 feet and 32 feet on the upper end, but there's still potential for that area to have problems again, because we just need bigger ribs in that area. It needs stronger support. And so I've recommended to the Forest Service that they consider rehabbing that whole area just so we can open it up and restore that integrity of the tunnel, because that's the primary area of the tunnel that gives us problems.
Right. So, there's all this talk about the tunnel's integrity, and there is an exploratory process and way to consider alternatives for the future. But as far as the status of the tunnel right now, it's not in danger of producing like a catastrophic failure or a massive flood or anything. Can you give us just kind of like a status
No,
check for people who might be worried?
yeah, the tunnel's in good shape. It's performing well. The gate at the upstream end, the intake gate, is old and needs to be replaced, and we're in the process of replacing that gate with a contractor. The construction season is so short up there at Mount St. Helens. We can only do so much each season, and so it won't be till the summer of 26 that the gate actually gets replaced. And we're going to replace it with more than one gate now, so we have redundancy, resiliency up there. Initially, when the project was built, it was built with just one gate, and that's one point of failure, and we don't do that anymore. So the new design calls for a backup gate and safety gates for each of those gates. So we're going to have lots of gates at the intake to help protect people when they go in to inspect it, and have backups in case one gate fails. You have another one that will still work. So that just gives the project better flexibility and performs better over time.
And regarding the short construction season, can you just kind of give us an idea of what that looks like? And I know like you're probably not involved in the 504 landslide project, but that's another one in that area that has now been pushed back to 2027. And a lot of people are wondering, why do all these projects take so long? So can you just give a little more clarity on that?
Right. Well, the project is up between 3,000 and 4,000 feet. So when you're up at that elevation, you're in to snow, and the snow sticks around until the end of May, mid-June. So that means our contractors can't really mobilize onto the site until the end of June or 1 July. And the contract calls for the contractor to do all their work and be off the site, demobilized as we call it, by the end of October, no later than the end of October, because that's when the storm events start coming in, and snow will happen in September sometimes. So we have to keep a close eye on the weather, make sure everybody's safe and can get out of there. And the contractor's access for this contract for the gate replacement is along the Windy Ridge Road, which is a higher elevation actually. And that's where a lot of the snow is. And you can't get past that till it melts, or you can snow plow it. And so the contractor does, I'm sorry, the contract calls for snow plowing if needed. And so the contractor has to kind of gauge that and see what's most cost effective to get down to the pumice plain. And they built a construction road across the pumice plain over to the South Shore, where this summer they're going to build a barge facility that will facilitate mobilizing equipment over to the intake. The intake has no road access. The only access is by boat or helicopter. And so they're building a barge facility to float their equipment over, and they need a big crane, and they're going to dredge a high spot of spoils where wood gets hung up at the intake, and help with future maintenance there. And so all of those different actions that are required in the contract, you can only do so many of those each season before you have to demob. And so this season they'll put that barge facility in and do the dredging, and next season then they'll build a cofferdam and replace the gates at the intake. And then the following season will be demobilizing and deconstructing the road, because they have to reclaim that whole area they put the road in.
All right, I'd like to turn now to the sediment retention structure on the Toutle River. Um, you know, what led to that coming about? And can you also just remind us the year that it was completed?
Yes, it was completed in 1989, and it is the first congressionally authorized project for Mount St. Helens. All the work I've talked about previously up at Spirit Lake and is called the Mount St. Helens Protective Works, and it was all emergency response. And it did include, by the way, I didn't mention earlier, but the eruption, the landslide, caused the formation of two new lakes, Castle Lake and Coldwater Lake. And keep in mind the blockage at Spirit Lake as well as Castle Lake and Coldwater Lake are not engineered blockages. They're just a mound of material. And we have to monitor those very closely and make sure there's no failure that might happen. And so for Coldwater and Castle, it was a different situation than Spirit Lake in that the Corps went in and just bulldozed an exit channel, if you will, and made an outlet for both of those lakes that's gravity fed. And we monitor those still today when we do inspections up there. It was Spirit Lake that was the big one that had to be figured out and ultimately resulted in the tunnel. So we were doing all that emergency response work. At the same time, Congress was putting the legislation together to authorize the Corps to manage the sediment because everybody was warning Congress there's a whole lot of sediment that's going to be coming off the mountain. In fact, during the original eruption, that sediment, the mudflow, went all the way to the Columbia River, and it filled in the nav channel, so it was only 13 feet deep and stranded ships in the channel. And that was part of our emergency response, was to dig those ships out and open up at least one lane of the nav channel. And that's a big deal because the Columbia River, a lot of commerce goes up and down the river, and that was very important. So Congress knew that we had to address sediment coming down and try to get a handle on that. So we had control over what was going on in that nav channel, as well as the level of flood protection for the communities downstream, because the Cowlitz and Lower Toutle, they had all filled in with sediment, and their level of flood protection from the levees was gone. And so the Corps had to go in and dredge those channels out. And we actually raised the levees 3 feet to provide the authorized level of protection for them. So the long-term management of sediment involved looking at alternatives. And we looked at smaller check dams, if you will, up in the upper reaches of the North Fork and the South Fork. The North Fork was the primary target. They got hit hardest in the North Fork, but there was still sediment coming down the South Fork. So the Corps did a check dam we call N1 for North Fork and S1 for South Fork. And they were different technology. We used roller compacted concrete called RCC for N1. It was brand new technology at the time, and we wanted to see how well it would stand up to all the sediment and the abrasion and erosion that was anticipated. And it performed pretty well, but it was a low head dam, and it quickly filled in with sediment and was overtopped, but it proved that technology. Over on the South Fork, they tested gabion baskets, which are just wire mesh baskets filled with gravel. And then they sprayed concrete on, we call it shotcrete. And they tried to see how that withstood the forces of the sediment coming down. It didn't perform as well. So we were leaning more toward RCC. And that technology got incorporated into an idea of building a sediment retention structure, and it's not called a dam because it's not like all other dams in the country where you have a reservoir behind it and it's used primarily for flood risk management. In this case, this was to retain sediment. So it's a sediment retention structure. We had a team of people that actually flew over to Japan and looked at what they were doing there because they had a very similar situation with volcanic eruptions there. And they took some of that information, that technology, and brought it back over here and incorporated that into the design of the SRS, and primarily in the outlet works, where we had a series of pipes. I think it was 5 or 6 rows of pipes that as water and sediment built up behind the dam or the structure, it would flow through the first row of pipes, fill with sediment, and you'd close off that first row of pipes and raise it to the next row, 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 until you're all done. And then the water would be permanently diverted through the spillway. And so the spillway at the SRS at the crest is 400 feet wide. That's huge. And the reason it's so big is it's designed to handle a mud flow. And that was the driving design criteria for the SRS. What if the Spirit Lake broke out? The mud flow would result in a certain amount of material and flow coming down the Toutle, North Fork Toutle in particular. And so the SRS was designed not to stop the mud flow, but to slow it down and help it settle out a lot of material before it made its way down to the downstream communities. So that's where RCC comes in. The SRS is an earthen dam, but they armored it with RCC on the upstream face. So if that mud flow came roaring down the North Fork, it would hit that RCC, hard concrete, and it would flow laterally across the face of the dam, hit a round pier nose wall, and the flow would be split between the spillway and the outlet work, slowing it down and letting the sediment settle out, and then have it go down the spillway and downstream where more sediment would settle out, but hopefully slow it down and take some of the load out of the mud flow before it hit the downstream communities. So that's the basic design of the SRS. It was originally designed to be taller than it is right now. And when we did a value management study on that, we decided we don't have to build the whole structure right now because it could be, we don't know how many years in the future we're going to need the full height of the SRS, if at all. So let's build it up to a certain height. And so it has a really broad crest right now. And that's so if we need to, we can go back in and raise it to a higher level and store more sediment and protect the communities downstream. And so that's what they decided to go with. They did look at, like I said, a series of check dams all through the system versus one big dam. And they looked at dredging as a permanent solution. That was way too expensive. Where are you going to put all that material? You know, that those kind of issues. And so actually the decision was to build the SRS along with dredging as needed in emergency cases, and to raise those levees downstream to give the level of protection. So it was kind of a threefold attack on sediment management. And that's what's been in place ever since. And they're just now, and that was for like a 50-year horizon, which took us to 2035. And so the Corps, I think, will be looking at that next phase of this project, what happens after 2035 and beyond. And I think they've expressed capability to do that study and analysis. I don't think the funding's in place yet, but that's the next step in the sediment management that I'm aware of.
You mentioned once all the sediment went down into the shipping lanes of the Columbia, it left it 13 feet deep. For perspective, how deep is it normally without all that sediment? Do you know?
I believe back then it was 43 feet.
Okay.
And so it went from 43 feet to 13 feet. So it really filled in rather quickly. And that was right where the Cowlitz empties into the Columbia.
Okay.
And so there were ships in the channel and they were stranded, stuck in the mud, so to speak.
Last thing I want to touch on is, this is a really big thing with a lot of things to consider. You have all the communities downstream at risk from flooding and the issues from the sediment. You have Spirit Lake and what could possibly happen within the future. How do you balance those needs of the populations with also the natural recovery of the area and, like restoring fish habitat if fish can't get up the Toutle River to spawn because the structure's there?
Yeah, the primary thing to consider is life safety and property, right? That will always rule. If there's any risk, that's going to decide, what to do. But basically what you go through and what the Forest Service and their consultant are doing is going through a risk analysis. So you look at those things that are, detrimental to life and property, but you also look at other criteria such as the environment, the fish, and cultural and everything, all of those aspects you mentioned. And all of those are evaluated per alternative. They have a number of alternatives they're looking at, and each one is evaluated on the risk, both during construction and then afterwards during implementation and operation. What does that look long term? And so they'll do that risk analysis for each of the alternatives, and they can even weight some of the criteria, like you know, people's lives and their property would be higher rated than other things, so to speak. That gets a little dicey when you start weighting criteria, but that's what's important, is to do that risk analysis, to do a fair and balanced assessment, impartial assessment of each alternative. What do you get for each alternative? What are the impacts of each alternative? What's the cost of each alternative? Of course, cost is a big factor. And then you go from there. And they have just published in the Federal Register their draft EIS, I believe, for public comment.